The last thing that we will discuss in section 9.1 is an application of the ellipse. We want to first define a term known as eccentricity of an ellipse. Given an ellipse with major and minor axes of lengths 2a and 2b, respectively, the eccentricity of the ellipse, denoted by the symbol E, is defined to be E is equal to C divided by A. In other words, the square root of A squared minus B squared divided by A. If E is equal to 0, then C is equal to 0, and the ellipse is a circle. At the other extreme, C may be close to, but cannot equal A, in which case E is close to 1. An eccentricity close to 1 indicates a relatively skinny ellipse. Now, we're going to look at an example of how to use this, but I want to point out a couple of things to you. First of all, in our formula, E is equal to C divided by A. Recall that we have highlighted in green this formula, A squared minus B squared is equal to C squared. And so all they have done is taken this formula and solved the formula for C by taking the square root of both sides. And so that's how we're saying here that C is the same thing as the square root of A squared minus B squared. The other thing I want to point out to you is this statement that says that if E is equal to 0, then C has to be 0. Recall that the only way for this to equal 0 would be to have a 0 on the top of that fraction. And in that case, you're looking at a circle, which is a certain type of ellipse. We also want to introduce what is called Kepler's laws of planetary motion. And again, we're going to read through these, but we're going to come back and look at what we need to work a particular problem. The first one says that the planets orbit the sun in elliptical paths, with the sun at one focus of each orbit. Okay, this is predominantly the one that we're going to use in just a couple of minutes to look at a problem. A line segment between the sun and a given planet sweeps out equal areas of space in equal intervals of time. And number 3 says the square of the time needed for a planet to complete a full revolution about the sun is proportional to the cube of the orbit's semi-major axis. Now, most of this we are not going to see being applied in this section, but they put the entire law here so that you can read through it. Okay, so let's look at how this plays out in a problem. All right, so our problem says that given that the furthest Earth gets from the sun is approximately 94.56 million miles, and that the eccentricity of Earth's orbit is approximately 0.017. And we want to estimate the closest approach of the Earth to the sun. So in our solution, and we're going to look at what this actually means in just a second, but we know that the first law, the one that we starred, says that each planet follows an elliptical orbit and that the sun is positioned at one focus of the ellipse. Okay, so let's go ahead and take that first sentence and just look at a picture, and then we'll come back. So we know that the planets follow an elliptical orbit, meaning that we have an ellipse, and that the sun is positioned at one focus of the ellipse. All right, so this is basically what we have happening. We have our center of our ellipse being maybe right about here. This is our focus. And it's also the sun, because we know that the sun sits at one focus of the ellipse. All right, and this blue dot is the Earth. And so the Earth is rotating around the outside edges of the ellipse. The next sentence says, thus the Earth is furthest from the sun when it is at the end of the ellipse's major axis on the other side of the center from the sun. Okay, so what that means is that the furthest position of the Earth from the sun is where we have the dots in the picture. All right. As the Earth moves around, it only gets closer. For example, if the Earth was here, this distance to the sun would be closer than the distance that we have here. And if the Earth is here, then its distance to the sun is even closer. So if we want to look at the furthest distance away between the Earth and the sun, then it has to be positioned here for the Earth in relation to that focus. And we know that that furthest distance is 94.56 million miles. All right, we have that in our problem, given that the furthest Earth gets from the sun is approximately 94.56 million miles. Okay, so let's go ahead and see what we can do in terms of working this problem. All right, so one thing that I know for sure is that this distance from focus to vertex on the Earth is equal to 94.56. So what I want to try to do is write an equation to represent that. So remember that this is a vertex point here. All right, and remember that when we're talking about an ellipse, the distance from the center to the vertex can be represented by A. So we know that this distance is going to be A. And we also know that the distance from the center to the focus, that we use a C to represent that center to the focus. So basically what we have here is an equation that can be written. We could take the A plus the C, and we should have that equaling 94.56. All right, so we want to keep that in mind, that that is one equation that relates focus to center to vertex to that 94.56 million miles that we were given. Okay, we also have a formula for the eccentricity of the ellipse. All right, so we are told that the eccentricity is 0.017. 0.017, and we know that the formula for eccentricity is C over A. So now what I have are two formulas that both relate the A and the C. So I can treat this kind of like a system of equations and try to go in and solve for the A and the C. All right, so what I'm going to do is I'm going to take this equation. It doesn't really matter which one you use, but I'm going to use this one because it has a fraction, and I'm going to eliminate that fraction by multiplying both sides by A. Remember that one way to solve a system of equation is by using substitution, in which case you take one of your equations and solve it for one variable. So I'm going to multiply by A, which is going to give me 0.017A is equal to C. Now I'm going to come to my other equation and substitute that in. So in place of the C, I'm going to put 0.017A. Okay, so in place of that C, we're substituting in. Okay, now we're going to solve it for A. So remember that this has a 1 in front. So 1 plus 0.017. Those are like terms, so we can combine those two. And then we can divide both sides by 1.017. Okay, so putting that in my calculator, that is going to give me 92.9, if I round to 2 decimal places, 92.98 for the A value. Okay, now I can go in and find the C value by substituting back into either of my equations. So I'm going to come back to this equation that I've been using. This A plus C is equal to 94.56. I'm going to plug in my A value. And then subtracting the 92.98 from both sides. Gives me a C value of 1.58. Okay, so now I know that the distance from my center to my vertex is 92.98, and the distance from my center to my focus is 1.58. Now, the next thing we need to do is actually look at the question that we're being asked. We want to estimate the closest approach of the Earth to the Sun. So let's go back to our picture. We want the closest approach from the Earth to the Sun. Well, where is that going to happen? Where are the Earth and the Sun going to be closest together? When the Earth comes all the way around and it is directly on the other side of the Sun, this is going to be my closest distance right in here. And so I need to determine what that distance is. Well, I know that the distance from my center to this point on the outside, I know that this is A. It's going to be the same as what we had on the other side. From center to that vertex or center to that vertex is going to be A. So if I take A and I subtract off the C, it's going to leave me with this little piece between the blue dot and the yellow dot. All right, so I'm going to do that. I'm going to take the A and I'm going to subtract off the C. So that's going to be 92.98 minus 1.58. And so that closest distance that we are trying to find is going to be 91.4 million miles.